classical mechanics, we're moving on to work energy. Now there's a bunch of stuff here, and it's kind of hard for me. I was trying to figure out how to break this up into one video, and I think what I'm going to do is to give a kind of derivation for the work energy principle, and then look at work done by a constant force, work done dropping a ball, work done by gravity, and then real gravity. And then we'll do another video later, because there's a bunch of stuff and really awesome things too. So let's get to it. Now, one of the things that we kind of need is the dot product, because we're going to deal with force and displacement. Both of those are vectors, whereas as kinetic energy, for instance, is a scalar. So just in case you can't remember, and this is I'm only doing 2D. This all works in 3D, but I'm doing 2D just to make things easier. Okay, number one, I'm going to stand right here. So suppose I have a vector A, and it has x and y components in the Cartesian coordinate system. So A is ax plus ax x hat plus ay y hat, and then I have another vector B, bx and by. We define the dot product, or as some people like to call it, the scalar product. I'm fine either way. Some people say, well, we use a dot, so it's a dot product. And other people say, well, you get a scalar value, so it's a scalar product. It doesn't really matter what you call it, okay? But it is what it is. We define the dot product as an operation between two vectors. Because remember, multiplication is an operation between scalars, and we have different variables. We have these vectors. So we define the dot product as the following. So if I have the vector A and B, then the dot product is the multiplication of their x components, so ax times bx, plus the multiplication of their y components, ay times by. Notice that because ax and bx and ay and by are components, they can be positive or negative or zero, and so that means that your dot product is a scalar, and it can be positive, negative, or zero. Okay. Also, since ax times bx is the same as bx times ax, I can switch that. Scalar multiplication commutes. Well then, because of this, the scalar product, the dot product, also commutes. So a dot b is b dot a. Now, there is this other definition that is sometimes useful. It says that the dot product is the sum, is a product of the magnitudes of a and b times the cosine of the angle between those two vectors, cosine of theta, where theta is the angle between those two vectors. Okay, so we're not going to do a lot of that, but I just didn't want to move forward and you'd be like, wait, what's a dot product? Dot product. And hopefully you've seen that before, but if you haven't, welcome to the world of dot products. Okay. Now, I want to start with a plausible derivation of the work energy principle, but it's not, okay, because it starts with the definition of kinetic energy. So I'm going to do this, and then I'll talk about kinetic energy and which came first, the chicken or the egg. That's what the problem that we're in right now. So we define kinetic energy as you have before, hopefully, 1/2 mv squared. Now, you probably didn't do that. You probably didn't say T, right? You probably said K or KE, but T is 1/2 mv squared. That's what we call the kinetic energy. In classical mechanics, we often use T for kinetic energy, and I think it's a French thing. I don't really know, but you know these words. Why do we use P for momentum? It's some Latin thing. I don't know. Just stick with it, okay? Now, let's just write. Remember, velocity is a vector, but we're squaring it. So you could write this as 1/2 m, the magnitude of the velocity squared. But the magnitude of the velocity squared can also be written as 1/2 m vector v dot vector v. You get the same thing, right? Because I'm going to get vx times vx, which is vx squared, plus vy times vy, which is vy squared, which is that. Okay. So that's my definition of kinetic energy. That's one definition of kinetic energy. Why is my camera doing that? Don't do that. Okay. So now let's take the derivative of the kinetic energy with respect to t. dt dt. I like that. It looks okay. If I do that, the mass is constant. But I do have a product, so I need to take the derivative of that times that plus this times the derivative of that. So I get 1/2 m dv dt dot v, right? That's still a vector, and I'm still going to have the dot product, plus 1/2 m v dot dv dt. But since the dot product commutes, dv dt dot v and v dot dv dt are the same. So these two terms are the same. So if I add them together, I have 1/2 and 1/2 is 1. So I get m dv dt dot v. Now, if I consider there's just one force on the object, or even the net force, it doesn't really matter. The net force, we could say F net is equal to ma, but that's a. That's the acceleration, that's ma. So this is equal to F dot v. So I have dt dt is F dot v. Now, as we've done many times before, I can separate this. I can multiply both sides by dt, and I get dt. I know I'm saying dt twice, but you gotta watch. You gotta watch, okay? dt is F dot v dt. Now, you could consider this power, just letting you know, because the rate of change of energy with time is power, and power is Fe. Okay, that's fine. Now, if we go to the definition of velocity, velocity is defined as the change in position with respect to time. So v dt is dr. So this is going to be equal to F dot dr. And there we have it, right? Because now if I integrate both sides, I get over here the change in kinetic energy, and we call that the work. So this is the work energy principle. I'll write it up here because it's important. Work is the change in energy is equal to the integral of F dot dr. Now, this, you may say, well, what about the potential energy? We haven't gotten to potential energy yet. Okay, potential energy is a trick that we'll introduce later, but this is the work energy principle. Now, it's not a real derivation because we started with the definition of kinetic energy. And where does the definition of kinetic energy come from? Well, a lot of times you can derive this from the kinematic equations, but I'm not going to do that. Okay, but you do see this connection. It's important to see that connection. Now let's use this. Let's use the work energy principle. Let's look at a special case. A special case. And first of all, this is an indefinite integral, so let's do this from point 1 to point 2, which doesn't make sense at this point. We'll do that later. What if f is constant? What if f is fx x hat plus fy y hat, and these don't change? They're constant. Well, in that case, then I can actually pull this constant value out of the integral. And it looks weird, but I can say work, I'm going to call it work. It's going to be f dot the integral from 1 to 2 of dr. Well, the integral of dr is just going to be f dot r evaluated from point 1 to 2. This is going to be f dot r2 minus r1, but that is delta r. So this is a really useful thing, right? This says that if the path makes sense, which it doesn't always, we can do this with non-constant paths, but right now we're dealing with a constant path. So in some cases, and a lot of times you'll see this in introductory physics, is that we'll define work as f dot delta r, where delta r is the displacement going from point 1 to point 2, and f is the force. Okay, I want to go and do this for a special case. I want to take a ball and let it fall and do it two ways. I want to do it using this. I want to calculate the change in kinetic energy, and then we'll set it up as an integral. And then we'll do it for a case where the force is not constant, and then we'll stop. Okay. Okay, let's check and make sure it's still recording. Because sometimes I get the question, is it recording? I don't know. Am I just talking to nobody, or am I talking to myself? You never know. Okay, so here's the situation. I'm going to take a ball at position, let's just call that, let's call that y1, and it's going to drop down here to y2. And I'm just going to find the change in kinetic energy. Well, as this ball, here's the ball falling, it has a force F equals mg, which is going to be equal to 0 x hat minus mg y hat. That's the gravitational force. I put the 0 there just to be explicit. And it's constant. What about delta r? Well, delta r is going to be r2 minus r1. And let's say these have the same x value. So I can write this as 0 x hat plus y2 minus y1 y hat. And that's going to be a negative number, right? Because y1 has a larger value than y2. It's going down in this case. Okay. Now I know F. I know delta R. I can just say work is F dot delta R. And so that's going to be the x components multiply each other. I'm going to do it explicitly. 0 times 0 plus the y components. Negative mg y2 minus y1. And so that's equal to the work. So the work is equal to negative mg y2 minus y1, and that's the change in kinetic energy. Now you say, well, that's negative, that's not right. No, it's positive, right? Because y2 minus y1 is a negative number, and there's a negative number right there. So be careful with the negatives. And this would be a positive change in kinetic energy. This says that it speeds up as it falls, which we already knew, right? And you could write this as 1/2 mv2 squared minus 1/2 mv1 squared. If you want to find the final velocity, you can, but I'm really focusing on the integral right here. That's my answer. That's what I want to look at. And I'm going to write that over here. Work is negative mg y2 minus y1. I'm going to put a box around that because we're going to come back to that. We're good? I'm doing my other things. So it should there it goes, thumbs up. Okay. I like the thumbs up. Okay. Now let's do it let's just do it as an integral. Because just for practice. And we're going to do some more complicated integrals later. So again, I have this. The force is negative 0 x hat minus mg y hat. And I'm going to say the work is the integral from 1 to 2 of f dot dr. Now, here we have to be careful because I have made this mistake more than one time. More than one time. Okay. Don't confuse delta r, the displacement, with dr, the integration variable. Dr in Cartesian coordinates is always going to be dx x hat plus dy y hat. And then the mistake I made, don't make my mistakes. The mistake I made was say, oh, it's moving down, so it's negative. No, it's not. We're going to do the negative. The negative comes in, the direction comes into play with the evaluation of the integral, the limits of integration. I have f, I have dr, so I get f dot dr. I'm going to write it explicitly. 0 times dx plus minus mg. That one does have a negative, dy. And so that's 0. Now I can integrate. Work is the integral from 1 to 2 of negative mg dy. And I've been kind of nebulous about these integrations, right? The limits of integration. But in this case, we can see we're actually going from y1 to y2. It's going to get more complicated than that later. But that's all I have to do. My integration only depends on y anyway, so it's not that bad. So it's going to be equal to negative mg, and then I integrate over y, or dy, I get y, from y1 to y2. So work is negative mg y2 minus y1. Identical, which it should be, right? Okay, so we've defined work, the work energy principle, and we've done it for a simple case with a constant force. We did it 2 different ways. We did it set up as an integral, but that was a boring integral. Let's do a fun integral, and a useful one too. Okay, and then we'll stop. Now, of course, if you drop a ball near the surface of the Earth, the gravitational force is constant. But if you drop it far from the surface of the Earth, the gravitational force is not constant. So here's the Earth. Let's say it has a radius of capital R. And I'm going to go from here, a point R1, the magnitude, is 3r to 2r, like that. And in this case, we have to use the real gravitational force. So I'm going to write this as a vector. F is negative g mass of the Earth. I'm going to use it as I'll call that mass of the Earth over the magnitude of r squared r hat. So this is in polar coordinates, or it really should be in spherical coordinates, but it doesn't really look any different right here. So if I have a ball right there, the force is that way, and this is the vector r. And I can write the vector r in polar coordinates, which we did before. R is r hat. And so if I want the dr vector in polar coordinates, dr is going to be dr r hat. And I skipped over why that's true, but we've done that before. You could, if you wanted to, if you don't like that, you could call this the x direction, and you could do it as, or y, and you could do it that way. But I'm going to use r because that's what it really should do. So now we need to set up, we need to calculate our work. So remember, work is the integral from point 1 to point 2 of f dot dr. So let's do f dot dr. F dot dr is going to be equal to this force dot that. And you'll notice that they're both in the r hat direction. So I just get, negative, I've made this mistake before, so I'm stopping for a second. Negative g m mass of the Earth over r squared dr, a scalar value. Now I can integrate. Work is, I'm actually going to pull all these constants out front because we can do that. Negative g mass of the object, mass of the Earth over, no, not over, I got to leave it in there, from r equals r 3r to 2r, right? So I'm going from r1, which is there, to there. And then I have 1 over r squared dr. So my integral only depends on r. I can integrate that. It's not too bad. So I get negative g mass of the Earth times negative 1 over r from 3r to 2r. And if we evaluate the limits, I kind of poorly managed my space here. Classic move by me. I get work is g m me, and then I have the final position, 1 over 2r minus 1 over 3r. And notice that this is a positive number, right? Because I'm dividing by a smaller number minus dividing by a larger number, so it's positive. So I do get work as positive. I do get an increase in kinetic energy that's positive, which is good. Now, if we want to, we could put in our values for g, for mass of the Earth and all that stuff, and find out what the speed is. But the important thing is we did an integral. Okay? We didn't have a sign error. We know that it has to be speeding up, so that's fine. And it was with a non-constant force. But again, in both situations, I'm moving in a straight line in direction with the force. What happens if those are not the same? That's what we're going to do in the next video. So you have something to look forward to. Okay, so that's your introduction to the work energy principle. We'll do more line integrals later. I'll talk to you later. Thumbs up, a double thumbs up, a double. There we go. See, I can do that when I use this QuickTime to record. I'll talk to you later. I already said I'll talk to you later. Okay, bye.